In this video, we'll be looking at how to interface with an accelerometer sensor and write an I2C driver from scratch for an STM32 microcontroller. We'll only be using the datasheet, STM32CubeIDE as our development environment, and the hardware abstraction layer. I'll be hooking this accelerometer, this ADXL355 you see on the left, which I made a breakout board for, to the board on the right, which is the LittleBrain board I featured in previous videos, which contains an STM32 F4 microcontroller. So let's get started. The boards you just saw were produced and assembled by JLCPCB in China. This is also where I got this ADXL355 accelerometer from. As you can see, it's actually quite expensive, and it's a reason why I chose it. It's a low noise, low drift and low power, 3-axis MEMS accelerometer, and I thought that'd be quite interesting to give a little try. So we're going through this datasheet you see here, figuring out what is actually relevant for us to write a driver, what information we need, and then how to convert that into an actual driver in the STM32CubeIDE development environment. So we'll go through pretty much the whole process. If you'd like to look at the schematic, for example, for this LittleBrain board, you can go to my GitHub page at github.com/pms67, click on repositories, and then you can navigate the LittleBrain sensor board repository. I have everything with the firmware in there, the hardware files, assembly files and Gerber files and so on, so you can actually get this board manufactured yourself. But we're referring back to the schematic throughout this video. A big thank you also to Altium for sponsoring this video. I use Altium at my work and also my spare time for more complicated designs. You can see Altium in action, for example, this RP2040 video. Altium is actually offering a free trial version of Altium Designer. I'll leave the link in the description below this video, but you can also go to altium.com/altium-trial-flow. Before we get started writing the driver, let's look at the ADXL355 breakout board schematic, which consists of roughly 3 sections, which is basically an input filter and regulator, the accelerometer itself, and a header where I break out all the pins from the accelerometer, for example, SPI, I2C, and so on. So for reverse polarity protection, I'm using a P-channel MOSFET with a Zener diode and resistor capacitor, just for some protection of the gate. Then I have this Pi network, which is a ferrite bead and 2 capacitors for some filtering. And lastly, this 3.3 volt regulator with the relevant decoupling capacitors. Then the accelerometer is very, very simple. Basically, all this accelerometer needs, according to the datasheet, are some decoupling capacitors. And I've created this symbol and footprint myself. So here you can see all the decoupling capacitors, and we can get this from the datasheet. So first of all, we can get the pin configurations and function descriptions, which tell us what each of these pins do, and this is really useful. So what do we need to hook up, what can be tied to ground, and so on. And they actually usually give you an application circuit. So just a basic example circuit that will get this thing up and running. And that's what I've taken over and implemented in KiCad. Lastly, I have a header, just a simple, I think, 10-pin header. I'm putting power input and power output, the interrupt pins from the accelerometer, the SPI and I2C pins, and some current limiting resistors to protect the device, and of course some ESD protection to protect the device further. This accelerometer is quite expensive, and I don't really want to mess it up. So here we are on KiCad in the PCB layout editor as well. This is a simple 2-layer board. I've sectioned things in power, accelerometer, and header. So a very simple board, routed power. I've got a ground plane on the second or lower bottom plane, and that's about it. We can see in the 3D view, and this is also the board you saw at the beginning of this video. So really, really simple design, just to break out this accelerometer, and so I can interface it with different MCUs, for example. As I mentioned at the beginning of this video, I actually have the LittleBrain STM32 F4 sensor board files available in my GitHub repository, and we'll actually be looking at this LittleBrain schematic as a PDF file. Now I've scrolled to the microcontroller page, and this is where you can see the pinout of the STM32 F4 microcontroller. I've connected a 16 MHz high-speed external crystal. I'm using I2C1 to interface with the accelerometer, and I'll be using one of these RGB LEDs. Then I also have a USB connector, which I'll be using to power the STM32 F4 board, and also to interface, for example, via a virtual COM port. I'm also using serial wire debug to debug this program. I'll be using the STM32CubeIDE development environment, which is a free Eclipse-based IDE provided by ST to program their STM32 microcontrollers. Now in STM32CubeIDE, I've created a new project, selected my part, which is an STM32 F405, and already done the pinout. So let's get through what I've done. In RCC, I selected my high-speed external crystal. Then in the system settings, I enabled serial wire debug. Now I'm using it with the SWO pin, which is the trace pin for extra debugging features, which is usually on PB3 for these microcontrollers. Then I've enabled I2C, and you can do that by either clicking on the relevant pins and selecting SCL and SDA. On the left-hand side, in the dropdown, you can also select I2C1. I've also enabled USB, which you can find in connectivity, and then USB full speed, and I'm using it in device only mode. Another thing to enable while we're at it is down there in middlewares, click on USB device, and I would like to use a driver for a virtual COM port, and ST provides this already, so we have to do minimal work. Then I've enabled an LED pin, which is just a GPIO output, and I can actually right-click on that pin and enter user label to give it a sensible name rather than, GPIO1 or something like that. The accelerometer also has an interrupt or data ready pin, and I can use an external interrupt GPIO. If I right-click and select the bottom option, that'll then fire and enable me to, for example, read the accelerometer values when this pin is set high by the accelerometer. In the NVIC settings, I also have to enable this line interrupt to make sure it actually fires. One more thing we have to do is actually set up our clock with our PLLs, and we can go to clock configuration. We enter our HSE frequency, which is 16 MHz according to the schematic. We select HSE and the PLL clock, and we type in our desired clock frequency, which I chose to be 168, which is the maximum. Then you can press enter and let everything be solved by CubeIDE, and then just click save to generate code. Now that we set up our CubeIDE, I've hooked my ADXL355 breakout board to the STM32F4 breakout board, as shown here, with an ST-Link connected. So here we are back in STM32CubeIDE, and we're pretty much ready now to write our driver for the ADXL355 accelerometer. So once you've completed your pin assignments and wired everything up, you can click up here on save, and this will automatically generate the basic low-level code we'll need to run this on our STM32 microcontroller. Then if we navigate over to our main function, you can see I've already done a tiny bit of work, and I'll walk you through it. So first of all, I've added this ADXL355.c file in my source folder, so you can simply right-click, click new, and then create source file, give it a relevant name. And we'll also need a header file, which has the similar name, so ADXL355.h. Again, right-click on the include folder, and click on header file, and give it an appropriate name. And this will form the basis for our C driver. So I'm going to be writing this in C rather than C++, but the choice is entirely up to you. In our .h file, this is our header file, we'll define everything. For example, register IDs, device IDs, what functions we have. And in ADXL355.c, our source file, we will then implement those functions. And finally in main.c, we will call those functions and include those driver files. So here I am in main.c, and these are the basic includes that STM32CubeIDE has generated. To use the USB virtual COM port, I also have to include this header file. And then again, I've already included the ADXL355.h header file, which we'll be writing in just a second. So let's go over to that. So here we are in the ADXL355.h header file, which I've already written. And I would like to just talk you through what I've done and why I've done it. First of all, it's always good to just include some sort of comment what this driver is for, who the author was when it was created. Of course, you can add much more detail, but this is a good start. Then we have this preprocessor directive. If not defined, this name, define this name. And at the end of the file, we will then have the relevant end if. And this is just to make sure that we maybe might include this file or this header in multiple places, ADXL355.h. If we use an include statement multiple times, we will not have the same code copied into our program more than once. Secondly, you will see that I have this include here, this STM32F4XX_how.h. And this is needed because we'll be calling some hardware abstraction layer or HAL I2C functions. I always recommend that you comment pretty much all of your code, even if it seems really basic or elementary. So we'll need this include to include some things like memory reads, memory writes, to and from registers. In my drivers, I typically like to include a define section. So I'll define things, for example, the I2C address, and certain things, for example, the sensor's device ID or part ID and so on, which we'll be checking later. Now, the I2C address you can actually get from the datasheet, of course. So let's go over to that. So this is the ADXL355 datasheet, and if you browse through the documentation or simply do a search with Ctrl F, you can see that we are detailing here the I2C protocol. But it also tells us about the I2C device ID. If you saw from the schematic of the ADXL355, there's an A cell pin, and we can pull that low or high, that'll actually change the I2C device address. So in theory, we could have two of these accelerometers running on the same I2C bus. I only have one, and I've pulled the A select pin low to 0, which gives us a device address of OX1D in hex. And you can see if I go back to STM32CubeIDE, that's what I've put in here. So AX1D is from the datasheet. And again, I've written a comment that if A cell is low, we get this address. If ASL is high, we get this address. And I've also written the relevant page of the datasheet in my comment. Now you'll notice here I'm actually left shifting this address by 1. And let me tell you why. So if we go back to the device configuration tool and to I2C, you can see that actually the primary address length is 7 bits. This is because actually we're using 8 bits, but the first 7 bits are the address, and the last bit, bit 0, is the read or write bit. That's why we have to shift this I2C address left to make sure the bit 0 is free for our write or read bit. Before we move on to the next section, there's usually always a register map in datasheets for sensors like this, and we have that on page 31 of the datasheet. So we have the ADXL355 register map. And this will tell us the address of each register, for example, 0, 1, 2, 3, 4, and so on, what the register name is, and what the register contents are, and the bits, and so forth, and if we can read or write, or both, for example. Also, when the sensor is first powered on, it'll have this reset state, or when the sensor's reset, and this will be the default contents of that register. This is going to be really useful for writing our driver because we can already see, okay, we can get the temperature data out here, we can get the x-axis accelerometer data out here, and so on. We also have some sort of setup registers down here, and we'll be going through which ones we'll actually use and how to write to them or read from them. So back in STM32CubeIDE, you saw that the device actually has a device ID, MEMS ID, and part ID, and that's given in the datasheet. If I go back and scroll a bit down, the first 3 registers are device ID, MEMS ID, and part ID, and these are fixed for this sensor. And at reset, they'll have OXAD, OX1D, and OXED as values, and that's pretty much what I just copied over here. Now, the reason for doing this is because at power up, or when I start up my STM32F4 board, I want to communicate with the sensor and check if this is the same, and this is the same. Just to make sure, first of all, does my communication work? Can I read the register and get the right addresses and contents out? And to make sure I'm connected to the right sensor. So I typically will do a device ID or part ID check at the beginning of my I2C driver. And I'll show you how to do that once we get to the writing the functions. Now below that, I've made my register defines. Again, I've put it in a comment which part of the datasheet that can be found. That's page 31. And that's the page we just saw with this register map. Essentially what I'm doing with my defines, if I go back, is I'm defining the name of my sensor, underscore that it's a register, and then the name of that register. And simply giving it the address, so starting from 0 all the way down here. If you're writing a really, really simple driver, you might only need certain registers. You might only need the device ID. You might only need the data registers and so on. But I've just included all of the registers from this device datasheet just to be complete. By writing the registers and defines, we can just reference, for example, the device ID register rather than writing OX00, and it makes the code clearer to read, and you'll see that in just a second. One thing I typically like to do with my C drivers as well is include a struct. And this struct I'll be creating an instance of in my main function, and this will be passed to my, for example, initialization functions or register read functions and so on. Essentially, this is really simple and it just stores the I2C handle. So if I'm using I2C1, I2C2, and that depends on my STM32 and my connections, this struct also stores the acceleration data, so not the raw, but rather processed and converted to meters per second squared. And I always typically include the units. Then I lastly have my temperature data in degrees C. This is a very simple example, but this struct might grow larger for more complicated sensors, and depending on data you want to store. Finally, we reach the end of our header file, which contains our actual function definitions. The first one here is our initialization function. I've given it the sensor name, and I've given it underscore initialize. As arguments, where I'm passing essentially the struct as a pointer, and the I2C handle we'll be using. And we'll be calling this from our main function. This initialization function essentially just sets up the sensor. It makes sure the device ID, part ID, MEMS ID, and so on are correct. We can set up our, for example, our output data rates. We can set up our low pass filters, high pass filters, and so on. Everything that's internal to the sensor will be set up here and checked. Now I'm returning a uint8, so 0 to 255, to give me essentially an error code. Next, we have these data acquisition functions. So I've, again, sensor name underscore, for example, read temperature, and as is quite obvious, this will return the temperature or give us the temperature reading from the accelerometer, and we pass the struct as usual. The second one is the read accelerations function, which reads the x, y, and z accelerometer values and converts them to meters per second squared. Again, we're passing the struct. Now you can see our return value is actually this HAL status type def. And this is essentially just because we're doing one single I2C transaction in each of these functions. This will give us if the HAL I2C transaction was successful, whether there was an error, or if the bus was busy, for example. In STM32CubeIDE, I can control click, and that'll show us this enum in the STM32 drivers. So you can see HAL OK, HAL error, HAL busy, or HAL timeout. That's quite useful for debugging. Lastly, what I like to do is just include very simple low-level functions. And these are just there to read the sensor's registers or write to the sensor's registers. So you have a read register function where I can just pass the address of a register and a pointer where I get the data out. And this is just 1 byte I'm reading. I also have a second function, which is read registers, which will read multiple bytes of data, starting from a certain register address, saving the data in this pointer, and given these number of bytes. Finally, I have a write register function down here, which does the same thing, just in reverse. So I give my struct, I say which register I want to write to, and what byte of data I want to write. And that's pretty much it. So now we've written our header file, we can move over to the ADXL355.c source file and then actually implement these functions. So we're going to write the initialize, we're going to write the lower level functions, and we're going to write the read temperature and read acceleration functions, of course, using the datasheet. So here we are in ADXL355.c, and first of all, we'll look at the lower level functions because we'll be using these in pretty much all of the other accelerometer or driver functions. We'll start off with the read register function. Again, we're passing the struct as a pointer, we're saying which register we want to read, and we're passing a pointer where the data that will then be stored, and we're returning the HAL status type def. In essence, this is just a rewrite of a function just to make it a tiny bit more elegant, a bit simpler, and I'm using the HAL I2C memRead function. Again, if I control click on this function, it'll take me to the relevant driver and I can actually see how it's written. And luckily ST has done this work for us. So all we have to do is look at what arguments it takes. So if the first argument is the I2C handle, then we have which device address, so this will be our sensor address shifted left by 1, the memory address, so which register you want to read, the memory address size, this will be 8 bits, then a pointer where we want to store the outcoming data, how many bytes we want to read, and what timeout we'll have in milliseconds, I believe. So if we go back to our driver, that's all what I've filled in. So I'm calling the HAL I2C memRead function to read a register. I'm passing the I2C handle we've stored in our struct. Then I'm saying read from our defined I2C address, which we defined in ADXL355.h. I'm saying I want to read the register we passed to this function. This is a define saying, okay, we want 8 bits or 1 byte of data to be read. I'm passing the pointer where I want to store the data. And I'm saying I want to read 1 byte of data, and I'm not giving it essentially a short timeout. I'm saying the HAL maximum delay is how long I'm willing to wait for this transaction to finish. Now, HAL I2C memRead actually returns the HAL status type def. So all I'm doing in this function is returning the outcome of HAL I2C memRead. So really, really simple, and essentially just a rewrite of the I2C memRead function. So I don't always have to pass I2C address, the mem adds size 8-bit, and how much data I want to read. For the read registers function, where I'm reading more than 1 byte, all I'm changing is that I have another argument, which is the length, and I'm passing that to my memRead function. And that's it. The write register function uses the HAL I2C memWrite function. So instead of memRead, it's memWrite. And again, I can control click and see, okay, what arguments does it take? And it's pretty much the same as before, other than the fact that I'm writing the data that's in this pointer here. And that's all I'm doing. Again, just rewriting the I2C memWrite function to be a bit neater. And that was it for the low-level functions. So really, really simple, thanks to the HAL that ST provides. With the low-level functions being written, we can actually now return to the ADXL355 initialize function. And if you remember back, this is where we actually set up our struct, we initialize our I2C handles, we perform sensor initialization, so for example, setting our output data rates, our filters, and so forth. So we take in the struct and we pass the handle from our main function. The first thing I do is then actually set the struct parameters over here. So I store the I2C handle as a pointer in the struct, so we don't have to keep passing this I2C handle at every function. And I set all my measurements to 0. Okay, so the way I sometimes do this, and this is a very, very crude driver, so there are much better ways of doing this, but essentially because I'm having so many transactions in this initialization function, so every time I read or write to register, I'll get a HAL status type def, I'm essentially adding up my errors. And this is my error number, which I start at 0, and every time I get an error, or busy, or timeout, or something, I'll add 1 to this. And finally, I'll return this error number at the end of the function to indicate to my main function, okay, this is how many errors I've had. There are much better ways of doing this, but for simplicity's sake, let's just stick with this. So the first thing I always do with the driver is actually check, as I said before, the device, MEMS and part IDs for this specific sensor. Again, this was on Datasheet page 32. I'm creating a variable where I store the resulting register data, which I then have to pass as a pointer to my read register function. So again, I'm calling my low-level function, which we just saw. I'm passing my struct. I'm saying, okay, I want to read from the register, which is called device ID, and I'm passing this variable by reference. Then I'm storing the status to see if it's HAL-OK, HAL busy, timeout, and so on. If the status is not HAL-OK, I'm adding 1 to my error numbers. So basically, I'm checking if this transaction goes all right. I'm reading this register and storing the result in this 8-bit variable. If the register data is not equal to my device ID, and again, my device ID I stored in my defines in ADXL355.h, so if the device ID isn't equal to OXAD, there's pretty much no point in continuing because we can't really talk to the sensor. That's why I just return 255 to indicate, okay, the device ID doesn't match. I do the same thing for example, the MEMS ID. So I read the register relevant to MEMS ID. I check if it actually is the MEMS ID. If not, there's no point in continuing. And a third try, of course, with the part ID. So this is just to check, does the communication work, and is this the sensor we actually want to be talking to? Now, once we've passed this point and we haven't returned from this function due to an error or something like that, and we could, of course, check if the error number is greater than 0 at this point, because then there probably isn't any point in continuing. But for now, let's just continue assuming as long as the device IDs, MEMS IDs, and part IDs are correct, we can then configure the sensor, and that's what we're going to be doing now. So here we are back at the ADXL355 datasheet and looking at the register map. So for initialization, we want to see what registers are actually of interest to us for setting up the sensor. So for example, the X data, Y data, Z data, for initialization, that's not important. We already checked the part ID, device ID, MEMS ID, and so on. What we might want to do now is actually look down here, for example, at the filter settings. So this sensor actually includes a low-pass filter and a high-pass filter, and we can set essentially the cutoff frequencies for those filters, as well as the output data rate of the sensor, and that's something that's pretty important for this type of sensor. We can also look at this sensor here to set what actually appears on the interrupt pins of this sensor. Another thing we can do is set the I2C frequency, and then actually get this device out of standby mode. In our case, just this being a really simple driver, all I'm going to do is set the filter high pass and low pass corner frequencies, as well as the output data rate, and then I'm going to get the sensor out of standby mode. So let's first of all look at the filter register, which is at OX28. And if I scroll down, I actually get a more detailed description of this filter settings register. Now it's addressed at OX28, which we've already stored in our defines in our .h file. And the default setting you can see here, which is OX00. That means, okay, the first bit here is reserved. That's the most significant bit. If it's 000, the next 3 bits, that means no high pass filters enabled. And the last 4 bits essentially mean, okay, we have a 4000 Hz output data rate and a 1000 Hz low pass filter corner. All right, so 4000 Hz output data rate seems a bit much initially for me, for my application I might want to use it for. I don't want a high pass filter. Okay, so let's see how we would want to maybe set these bits. So the first bit reserved, so that's just 0. Then I don't want to have a high pass filter in my application, so the next 3 bits are 3 zeros. And then I want to set my output data rate and low pass filter. So 4000 and 1000 seems a bit high to me. I'm going to want something much slower, for example. So I'm going to use 125 Hz as my output data rate and 31.25 Hz as my low pass filter corner. So that's why I have to set the last 4 bits as 0101. So overall, actually my bits are 0, most significant, then 3 zeros, and then 0101. And those are my 8 bits to give me 1 byte. So 0, 000, 0101. Now this is in binary and we want to convert this to hex. Now if you aren't that familiar with binary to hex conversion or the other way around, you can use something like a binary to hex converter, which you can just Google online. I'm typically use this rapid tables one. So I can enter my binary number, which I copied depending on the register settings I want, and then I click convert. Then I would like to set the register contents to be hex 5 or OX05. So if I go to CubeIDE, you can see that's exactly what I've done. I wrote in my comment that I don't want a high pass filter. I want 125 Hz output data rate and a 31.25 low pass filter cutoff. That's why my register data is OX05. So I set my register data, then I call my low level function to write the register, which is the reg filter, and I pass this register data. And this will make sure, according to the datasheet, that we have no high pass filter, we have 125 Hz output data rate and a 31.25 Hz low pass filter corner. And that's all there is to that. Finally, the last part of our initialization function is actually looking at this power control register, which is located at address 0x2D. Now, default, the reset value is 0x01, and let's see what that actually means. Okay, so the first 5 bits, so 7 to 3, are reserved, so they're all going to be 0. And the data ready off bit means essentially that there's not going to be a data ready output on that pin if we set this high, which we don't want. We want this data ready pin to go high when there's new data. And temperature processing, we don't want to disable, so this has to be 0, this has to be 0, and this has to be 0. But the last bit, by default, given by this reset value here, is actually 1. And if it's 1, it's in standby mode, so it won't actually do any processing and won't give it any measurements. That's why we have to actually change this 1 to a 0, because we want to put this sensor in measurement mode. So essentially, this whole register has to be 0 for this to turn on, to gather measurements, and to process temperature data, and to put a data ready on the data ready pin. So if we go back to STM32CubeIDE, you can see that's exactly what I did. So I'm writing 0x00 to put the sensor to measurement mode. Again, using the right register function, addressing the correct register, and passing this register data. Now, if this all goes well, this whole function, and we've passed the part ID, MEMS ID, and device ID, and so on, we can return the number of errors. Now, as I said before, if the number of errors is 0, we have a successful initialization, which we can check in our main function. And that concludes, actually, our initialization function. So now let's look at our first measurement function, and that'll be for reading the temperature data. So the accelerometer also includes a temperature sensor, which gives us uncalibrated temperature data. And essentially we can get these from 2 registers, which we have to combine and then convert to degrees Celsius. The address is at 0x06 and 0x07, and we can see how the bits are formed here. So for the first register, we have some reserved bits, and then we have 4 temperature bits, which forms the most significant part of the 12-bit temperature data. And then we also have this other register, which forms the lower 8 bits, or the least significant bits of this temperature data. We also see here the nominal intercept, which is 1852 LSBs, least significant bits, at 25 degrees C, which is essentially an offset. And we have a slope of minus 9.05 LSBs per degree C. So essentially we need to find out how can we read these registers, combine the information, and then convert that to sensible units, for example, degrees C. I have already written this function in STM32CubeIDE, the read temperature function, and I'd like to go through this, how I get from the datasheet to actually writing this code. So here I've written a little note of how I did it. So we're looking at the temperature data first, which essentially comes as 2 8-byte registers, where only 12 bits of those are actually useful. So we have temp2 here at 0x06 and temp1 at 0x07. Now the first 4 bits here are reserved, they're useless to us, and then we have another 4 bits, and then we have these 8 bits here. So 12 bits total, going from most significant to least significant. We want to read temp2 first. We don't care about the first 4 bits, but we care about the last 4 bits. So what we have to do, if we have a uint8t type, is actually AND this, so a logical AND, with a bit mask. So we can say 000. If we AND that with this, these will be all zeros. And if we AND 1111 with this, we'll get all of these 4 bits here. And then hex 0001111 is OXOF. So we have to read temperature 2 and AND it with this bit mask to extract these 4 bits. Then we have to left shift by 8 bits. So we have 4 bits here. If we left shift by 8, our register or data width will be 12 bits. And we have to store that in a larger variable, of course, so that will be uint16t. Then we can form our temperature raw, which is our essentially left-shifted temp2 register, and of course bit masked. And then we want to put the temp1 register, which is the lower 8 bits, or the 8 least significant bits. We're going to put that right next to it. And we can do that by logical OR. So we put temp1 here, and we put temp2 bit mask and left-shifted by 8 here. And we store that all in a uint16t variable. So if we go over to the code, that's what I do. I read essentially those 2 registers, starting from temp2 and then reading temp1, and I store that in reg data. Then I combine the register values to give the raw temperature reading, which is 12 bits. So I bit mask temp2, left shifted by 8, and OR it with temp1. Now we have to convert it to degrees C. The way we do that is, of course, from the datasheet again. We saw that there's an intercept at 1852 at 25 degrees C, and we have this slope here. Essentially, all we're doing is a linear mapping. So we have the offset and we have a slope. We want to go from LSBs to degrees Cs. Now, when temp raw is 1852, the datasheet tells us that the temperature in degrees C is actually 25 degrees. So therefore, we have to subtract 1852 from our raw reading and add 25. And that takes care of our offset. Then, of course, we have this slope, but they give it to us as least significant bits per degree C, we actually want the inverse of that. So we want how many degrees C do we get per least significant bit. So we just take the inverse and we find out it's some sort of constant. Then we can add these two together, so the offset and the slope, and that's how we convert our LSBs or raw data into degrees C. And that's exactly what I've done here. So I have my inverse slope and my offsets here. Now I could make this nicer by writing defines for this, this, and this, but this is just a bit easier to see or simpler to see for this video. And that pretty much concludes our read temperature function over here. Let's move over to the accelerometer function. For the raw accelerometer data, we actually have this x-axis data register, y-axis, and z-axis. But the procedure will be the same for x, y, and z, so I'm just going to show it to you for one axis. So we have 3 registers, 1 byte each, so 24 bits in total we have to read. Now, only 20 bits of this are actually significant data. As you can see here, the first data register, all 8 bits are what we want. The second register, all 8 bits are what we want. But the last register, only the top 4 bits are what we want. The last are reserved. We'll have to mask and then also bit shift. One important fact here is that it's actually formatted as 2's complement, and that'll be important later, because this will actually be a signed value that we get out of it. Again, let's look at some notes I made. Accelerometer data, we're reading 24 bits, but only 20 bits are significant for us, and we have to remember it's 2's complement. So here's the structure as usual. We have the most significant data first on the left, then we read our next significant data, and then we have our least significant data over here. So this is a whole register, this is a whole register, and this is a whole register. But for the last register, we are only interested in the first 4 bits of that register. Again, we'll have to use a bit mask to get rid of these bits. So the usual procedure, as with many drivers, is to bit shift, combine, and mask in a sensible order to form the raw data, which is then 20 bits. And again, this will be a signed integer, so I'm using an int32t type to score these 20 bits of data. So essentially, I can left shift the x data 3 by 24, OR it with my x2 data shifted left by 16, and then OR it with this data of x data 1 with my bit mask of OXFO, meaning 11110000, to extract these 4 bits, and then left shift 8. Once I've combined those, I've got a 32-bit signed integer, but I want a 20-bit integer, so I need to right shift by 12 to go from 32 bits to 22 bits. But I'm still storing it in an int32_t. Again, looking at the code for the accelerometer, I'm reading the registers for x, y, z, so 24 bits each, and storing in this reg data array. Then I have my raw signed variables of type int32t, 0, 1, and 2 for the x, y, and z axes, and I'm doing exactly that. I'm casting to the int32t, left shifting, bit mask and left shift, and finally right shift by 12. Exactly what I showed you in the notes. Then of course we only have raw values, and those don't really make sense because we want to convert them either to units of G or meters per second squared. So let's see how we actually do that. Again, if we look at the datasheet for this sensor, we can actually see that the default range for the ADXL355 is plus or minus 2.048 G. So all of our bits essentially map to plus or minus 2.048 G. We can write 2.048 G as 2 to the 11 divided by 1000. So 2 to the 11 is 2048. And we divide by 1000 to get 2.048 times G. We also need to know that the number of bits this maps to. Now we said accelerometer data is actually 20 bits, but because of the 2's complement, we actually lose one of these bits for the sign bit, which is the most significant bit. So actually we have 20 bits minus 1 bit, giving us 19 total bits. So 20 total bits minus the 2's complement or the sign bit. Another way of seeing this is that we have plus or minus 2.048 G. Essentially, half of the numbers are mapped to 2.048 and 0, and the other half of the numbers are mapped between 0 and minus 2.048. So essentially, our sensitivity, which is our meters per second squared, divided by our least significant bit, so how many meters per second squared do we get per unit, is our range divided by 2 to the power of number of bits. And if we work that out, we get a constant, which we then use to convert our LSBs or our raw data to the meters per second squared. And that's exactly what I've done here. Given the range setting of plus or minus 2.048 G, I do G times this constant and then times the raw data. And I do that for the X, Y, and Z axes. And that's pretty much it. Now that we've written a pretty crude driver for the ADXL355 accelerometer, we can go back to main.c and actually use our functions and include our driver and trying to see if this actually works. So as I said before, I've included my ADXL355.h header, and then I'm going to use the functions we defined in there. So the first thing I have to do is actually create my ADXL355 struct, and I'm just calling it ACK for short. What I've also set up is an actual external interrupt pin, which fires every time the data ready pin of the accelerometer goes high. So essentially every time it goes high, I set my data ready flag. So every time there's new data, I'll set it to 1, and I'll check in the main while loop if data is ready, and then I can do something with it. So here in our main function, I have to, of course, initialize the accelerometer, so I pass my struct that I defined earlier, and the I2C handle, which in this case is I2C1. I will also be printing data via the USB virtual COM port, so you have a little buffer here, and have a timer that just essentially counts at a fixed sample rate when I need to send data via the USB, and also when I want to toggle my LED. So initially I set my data ready flag to 0, and then I start my main while loop. So this main while loop essentially checks with this if statement if the data ready flag has been set by the interrupt. If it has, I read the temperature first, and then I read the accelerations. After that, I clear the flag so the interrupt can set it again. Now the constant sample time, which I've defined at the top of my file, I actually send the accelerometer readings and the temperature via the virtual COM port, and I can do that using these functions here. And lastly, I toggle my LED using these functions over here. But the main thing is that as soon as the interrupt fires, I set a data ready flag, I read the temperature, and I read the accelerations. So let's upload this to the LittleBrain board and actually see if we read the correct device part IDs, if the initialization works out, and if you read sensible temperature and acceleration values. So I have my LittleBrain board plugged in via the USB cable, as well as an ST-Link V2 connected to it. So I can click on this bug up here, which compiles and then uploads the firmware to my device. So let's go into the ADXL355.c file and actually set some breakpoints to see what's going on. So I'll just set one, for example, after our first check of the device ID, and then I'll check just before we return our error number. So let me click resume, and as you can see, okay, it's tried to read the register. The status is hello K, which is great, which means we can talk to the device. We've read the device ID, so let's see, reg data is set to OXAD, as you can see down here. Now let's check the ADXL355 device ID is actually OXAD, so this check will pass. So that's really good. So if we click continue, we can actually see we have 0 errors, all the writes and all the reads seem to work. So this sensor seems to be configured. Okay, so I'll just get rid of these breakpoints here, and now set new breakpoints in my read functions. So I'll do that just after I calculate my temperature in degrees C, as well as once I've converted to meters per second squared for my accelerometer values. So let me click resume and hope the interrupt triggers. There we go, it triggered, and I've read my temperature. So if I just hover over here, temperature is about 24.3 degrees, and that's about room temperature, so that seems about right. Let me hold my finger on the accelerometer and just resume a couple times, get some more measurements, and you can see the temperature actually went up to 25 degrees because I got my finger on it. Okay, so that seems to work quite well and seems to give a sensible reading for the temperature. That's good news. So if I click play again, let's check the accelerometer values. So I currently have the board flat on the table, which means I should get about 9.8 on the Z axis, and that's what I seem to be getting here. So let me rotate the board to one side, click resume a couple times, there we go. And you can see I've turned it to one side, and now the second here, this Y axis is now 9.8. That's really good. So if I turn it one more time just to check the X-axis, and here we go, we get about 9.8 on the X-axis reading. So it looks like our conversions work, reading the sensor works, our interrupt fires, and so forth. So it looks like our very crude driver is working. So thank you very much for watching this video. I hope it was helpful. Again, everything you need to write a driver is usually in the datasheet, also for doing the schematic and so forth. If you liked the video, please give me a thumbs up, and I hope to see you in the next one. Thank you very much.